Welcome back. In this video, I will talk about the vision transformer by discussing this paper. Before we continue, here is a quick recap of the previous video on the transformer, which I encourage you to watch for more details. In a transfer model, a sentence is first split into tokens, here words, and each token is converted into an embedding vector. Then attention heads are used to compute keys, queries, and values for each token multiple times. The dot product of the keys and queries is calculated to determine the alignment between tokens, and these alignment scores are used to weight the values. The result is an embedding vector enriched with contextual information from the entire sentence, capturing the relationships between all tokens. To use the transformer for image data, this paper first divides each image into patches of size p by p, where in this paper p is 16. For an RGB image, each patch has dimension of 16 by 16 by 3, resulting in n patches. These patches are then flattened, producing a matrix of shape n times 768. Then this matrix is transformed into a latent dimension of size d. To enable the model to perform classification or other specific tasks, the paper introduces a class token, a learnable vector that is appended as an additional row to this matrix. During training, the model learns to use this token to collect information from the entire image, allowing it to make predictions based on the global context. In addition to the class token, the model adds a positional encoding, which is another learnable matrix. This encoding is added to the input matrix to provide information about the spatial relationships between the patches. The resulting matrix is then passed through multi-head attention and dense layers in the transformer encoder. To use this output for classification, the model focuses on the class embedding vector, which is the transformed version of the class token. This vector is passed through a single multi-layer perceptron, which maps it to a vector of size y, where y represents the number of classes. Now let's implement this using Python, and to make it simple, I only process one image at a time, so there is no batch processing. I'll start from the init method. In this method, we pass relevant arguments such as the image size and patch size. We also calculate settings like the number of patches and sequence length. Now let's move on to the patch generator. This method takes an image, rates it and resizes it to a specific image size. Then we move along the rows and columns of the image and cropping patches of size 16. Each patch is flattened into a 1D array and added to the patches variable. Let's display some of the generated patches. After generating the patches, I transform the patches matrix to new latent space. Then I append the class token and add the positional embedding. These variables are initialized in the initiateWeights method. In the encoder method, we calculate the patch embeddings, and for each stack of our attention blocks, we compute the attention using the self-attention patch method. In this method, we first initialize the output for attention heads and compute the keys, values, and query matrices. We then calculate the scores scale the scores, apply softmax, and compute the attention by multiplying the result with the values. Then we concatenate the output for each attention head and pass them through a linear block. Then we apply 2 additional dense layers and we repeat the process for each attention block stack. Finally, after obtaining the last patch embeddings, we extract the first row corresponding to the class token. In the classification head, we transform it to match the number of classes for output. Let's see an example. First, the image is resized. We extract 256 patches, each with a flattened dimension of 768. These patches are mapped to a 512-dimensional space, and then we add the class token and positional vectors. Next, we pass the data through 2 stacks of attention heads, where we compute the attention output. Finally, the encoder output is passed to the classification layer to obtain probabilities for each class, and the class with the highest probability is selected. Thank you for watching this video.